My name is Ian Ferreira. I'm Senior Director with AMD, and it's great to be back at Ignite. I spent about a decade in a prior life working at Microsoft. And speaking of which, I'm going to give you a quick overview of the AMD software stack. And then we're going to have Gopi Kumar, who is in the office of the CTO, share some of their experiences using AMD at Microsoft. So before we dig in, I just wanted to give you an overview of the high-level stack. So where does ROCm fit in? If you look at the bottom layer, that's your typical GPU drivers. If you look at the top layer, that's your models, your ML frameworks, your Llamas, your PyTorch. And ROCm is essentially the stack in the middle that connects the ML frameworks with the GPUs. So if you look at our pillars or tenets for AMD's software strategy, it's really around being open. So people ask me, what's the biggest difference between CUDA and ROCm? And it's simple. ROCm is open source. So that's a very big difference. The second is around simplified programming models. We didn't want to reinvent the developer story. We wanted to keep the experience the same. So if you wanted to extend your cluster and add AMD or build a new AMD cluster, you wouldn't have to reteach or retrain your users. So the experience is the same. And last but not least, it has to be fast, right? Performance is a feature. So this is the ROCm stack. You can see from the bottom, everything from the drivers upwards all the way through the collective libraries, the math libraries, it's all open source. So it starts with GPL licenses at the bottom, and then makes its way up through APL and MIT licenses, all open source. And we'll talk a little bit about the work that Microsoft has contributed into ROCm. OK, so if you're using an ML framework, or if your customers, if you're in IT teams and your customers are using ML frameworks, it's drop-in. So on the left, you have CUDA code. On the right, you have ROCm code. And you can check me, it's exactly the same. Even the moniker for the device is still called CUDA. Arguably, we should have changed it to ROCm, but that will break the no code change rule. So you can see from the bat, there's a zero change required. You can take your notebook, you can take your Python file, and you can just run it on AMD. And so that's great when you have a cluster, because if the user ends up on a different server, that's OK. Their code will still work. If they end up on an AMD box, the code will still work. They wouldn't have to partition their code depending on which framework or platform they're going to run onto. OK, so let's talk about transitioning workloads. As I mentioned, in the ML framework stack, it's drop-in. So JAX, PyTorch, TensorFlow, Onyx Runtime, that will just work on AMD. If you're a little bit more sophisticated and you do your own kernel development, which is the microcode that runs on GPUs, if you're doing that in something called Triton, which is a very new language from OpenAI, that will also just work. So we have a Triton backend for AMD that will just work. If you're doing custom C CUDA kernels or PyTorch extensions, so there's a really advanced ML, those we have a tool called Hipify that allows you to move the workloads or the code from NVCC to HipCC, which then can compile both NVIDIA and AMD. And then obviously, if you're working directly with the low-level libraries, we have a symmetrical approach. So if you're looking for a cuBLAS equivalent, on our side, it'll be called ROCBLAS. So you'll easy to find your way around the stack. OK, so let's talk about the ML framework. So PyTorch, we're a founding member. We fully upstreamed. So it's probably 99% coverage with NVIDIA, and that's just a function of the time it takes for us to catch up with the very latest features. But all the FSDP, DDP, DP, multi-GPU multi-GPU workloads run out of the box. The same with PyTorch 2, Inductor, and Dynamo that works out of the box. And you actually download the AMD version from PyTorch themselves. So you go to PyTorch, get started, you pick ROCm, and you download the wheel file for PyTorch. TensorFlow works slightly differently. So you can really contribute directly into their code base. But they have something called SIG, Special Interest Groups. And this allows us to ship the TensorFlow for ROCm through that channel. Again, same support, multi-GPU, the mirrored, multi-mirror strategy, all that stuff works. Horovod Keras also works. And if you're using TensorFlow as serving, that will also work out of the box. So to install TensorFlow for AMD, you go to PyPy, you do a pip install TensorFlow ROCm, or you go to TensorFlow SIG. Last but not least is JAX. So JAX is the new kid on the block from an ML framework point of view. We have an optimized version for AMD. We are working to getting that upstream, but if you're interested in trying that, we have an image available on Docker Hub that you can use for JAX. It supports, again, all the features, Triton, PMAP, VMAP, PAX, which is the distributed model training framework. So switching gears to inferencing. Onyx Runtime, everybody familiar with that. We have 3 backends for that, ROCm, Vitis, and MI Graphics. Again, you can get this directly from the onyxruntime.ai website. VLLM, which is out of Berkeley, very popular right now. It's a fantastic inferencing engine, supports a lot of models, fully open source. This one's funny. We actually, in the process of open sourcing our version, but the community beat us to the punch, and they actually released a version for ROCm. So if you go to embedded LLM, you can get a ROCm version of VLLM, which is great for models like Llama. And then DeepSpeed, of course, from Microsoft. Fully supported, upstreamed, includes a lot of what's called injection kernels. This is how DeepSpeed intersects your model, distributes across GPUs and nodes, and it's also available directly from DeepSpeed's website. So we know, of course, it's not just the frameworks. There's stuff that happen upstream and downstream from ML frameworks. So if you look at data wrangling, if you're looking at GPU-accelerated NumPy, we have something called CuPy support. Dask and Ray, very popular as well, scheduling workloads. And then we're in the process of completing Rapid support. So that should be available in Q1 next year. Talked about the ML frameworks, distributed training. So if you're doing any sort of large-scale training, we have support for DeepSpeed, Horovod, Hugging Face Trainer, Megatron even, Mosaic or Databricks, and Colossal AI in China. Experimentation and ML ops, same thing, weights and biases, Run AI, all support AMD. So you don't have to have any changes in your ML ops stack. Talked about inferencing. If you're building an on-prem cluster, or you're building your own native cluster, in the cloud for Kubernetes or Slurm, you would need a Kubernetes device plugin. We have support for that. If you're doing Slurm, you need something called a gRACE plugin, which allows your cluster to schedule workloads. Of course, for data center operations, we have all the tooling, the management tooling. Instead of NVIDIA SMI, you type ROCm SMI, get the same data back. OK, so without further ado, I'm going to ask Gopi to join me on stage. Gopi is a principal program manager in the office of the CTO. And he's going to talk a little bit more about Microsoft's adoption of AMD. Gopi, welcome. Thank you.
Thanks, Ian.
So Gopi, from what I understand, Microsoft has been using AMD infrastructure going back to the MI100. Is that correct?
Yeah, actually, it goes back even further than that. So our journey with AMD began like long time back, like almost like 2019, when our researchers started taking a look at like Radeon cards, which was, I believe, the first card that actually supported like machine learning workloads in the ROCm stack. So they did some initial experiments, and then we were pretty happy with what we saw. And then we started a pretty close engagement with the AMD team and the AMD research folks. And as part of that, we onboarded a small lab cluster for our researchers to play around with. So that's a MI50 cluster. So this is about like 2 generations from the S1 current. And we did a lot of small-scale experiments. We did some framework porting, some of the frameworks that you talked about earlier. And I think we started prepping ourselves up to kind of do a real kind of a pilot with like real workloads, I think go beyond research. And that's where we onboarded a MI100 cluster in, I believe it was like somewhere around spring of 2021, so quite a while ago. So this is a mid-scale cluster. We're talking about a few, several hundred GPUs. And we wanted to experiment with it fast, so we kind of put it in off Azure lab. We again worked with AMD to kind of harden the stack. Like I think, like how do you really make it work seamlessly for like real workloads? And at that point, yeah, we started onboarding a few internal some pilots. Again, we wanted to test, like at that time, our focus was mostly on training. And obviously, we wanted to test distributed training. So we were able to run distributed training at the scale of like around 128 to 160 GPUs. And yeah, we were, as we were working through these, MI200 was quickly coming behind. And this is something we built it on Azure. And so we built it just like any other Azure SKU. And initially, it was internally only rollout, and this was a pretty large cluster. We are talking about a few thousand GPUs here, and the focus here is like really like performance optimization. So we wanted to bring the performance, establish that I think we can run it on par with some of the other hardware that we were using. And the other goal was to really onboard top tier workloads. We are talking about like the biggest workloads that we could find, have them run on this GPU, and also like measure. I think you mentioned something about like easily bringing in your software. We want to actually prove it with the actual software and the actual workloads, put it in the hands of the real data scientists, not just like researchers, like who can find their way out. So I think, yeah, this is kind of a real proof point. And yeah, we were like pretty happy. I think our cluster has been in operation since summer of 2022, and then we grew that cluster all the way to several 1,000 GPUs. Yeah, we are very happy with the reliability that we are seeing on that, on par with like I think meeting all the Azure standards that we have for scalability and reliability. Actually,
that's fantastic. So Satya mentioned this morning the top 500 submission. I don't know if folks know the top 500 is a leaderboard for supercomputers, and I believe that Microsoft did a submission based on the MI200, which is a prior generation. Can you share more about that?
Yeah, actually, yeah, I don't know whether there was an intention to kind of really submit, make that submission. But I think one thing we were seeing a very clear trend, like models are getting bigger, and we were training internally. We were training models across hundreds and thousands of GPUs. And obviously, we want to kind of prove that, like on the AMD stack, we can actually run these modern workloads. And so that's where as we started building this, like Azure and AMD worked like really close together, and built a highly interconnected cluster. So where like all these, like every GPU in this, like the few thousand that I talk about, they should be able to talk to each other. So this is like a fully densely connected interconnect. We use InfiniBand connection. And like each machine, like each GPU has access to like 200 gigabits per second. So that's a pretty high speed that you can train pretty much any model that you can think about. So as we were building this cluster, so we started running a whole bunch of benchmarks. And one of the benchmarks that we ran was the LinPack benchmark, which is like pretty popular in the HPC industry. And we ran those results, and we were pretty happy with the results. And this would have been one of the top cloud computers at the time we ran it. And we submitted the entry in June. So it was placed at, I believe it was like the 11th position among all the cloud public cloud systems. This was the biggest at that point.
Very nice.
And of course, yesterday or today, I think there's a new list. Even on this list, it is still like the 15th biggest supercomputer in the world. And in the cloud, I think it's the second biggest cloud computer. The first one is also in Azure, by the way.
Nice plug. That's fantastic. So you mentioned that the MI200 was internal only. Did you guys look at making those public Azure instances? Any comments on that?
Yeah, when we started this project, yeah, obviously I think there is a lot of, we wanted to first test it internally before we offer it outside to end customers. Obviously this is a new platform and people have to get used to this, the new software, and we ourselves needed to be kind of fully battle tested, so to speak. And I think our goal was to potentially onboard a few customer on a white glove basis before we open it up as a public SKU. And actually, like I think last.
You have a picture of it?
Yeah. So this is our cloud, and in fact, I think Kevin Scott, our CTO, he announced I believe at 2022 build that we are building this cluster. And the point of this announcement at that point was to potentially onboard like 1 or 2 white glove customers. But I think a lot of things changed. I think last November, I think we all had the ChatGPT moment. And I think if you remember, our initial focus was on training. But more and more, I think we started to look at inferencing and like fine tuning, like all these things became kind of a bigger focus. So at that point, again, we've kind of worked back with AMD and then figured out like how can this stack kind of handle both training as well as inferencing. So one of the reasons we kind of slowed down a little bit, did some performance optimizations jointly with your engineers, and also we wanted to onboard a few inference workloads. So we ended up kind of using all the capacity that we had to test both training as well as inferencing and fine-tuning, distillation. So we have a whole bunch of things that we ran. And also, one of the critical things is I think the whole stack has to work. I think before we offer, like I think we have a whole bunch of open source that we support. Like Onyx Runtime is something that we manage, DeepSpeed. So these are all like all these open source. We had to kind of get it up and running.
So that's a great point. I talked about the fact that AMD's tenant is for the stack to be open source. So Microsoft has a couple of software engineers. So I'm sure you guys have contributed. Can you talk about the work you've done as part of the open source?
Yeah, I think obviously like Microsoft is a pretty big believer in open source. I think I believe we are one of the top contributors to open source on GitHub. And we have a number of projects that are there specific to like machine learning, deep learning workloads. I'll just give you a little bit of a brief overview here. So the first one, I think we already spoke about Onyx Runtime. So here at the bottom layer, you see all the various execution providers that we provide. Like it runs on CPU. It's pretty popular for especially on inferencing. And I think about like 2.5 years back or so, we added support for training also. So we brought in the support for like the ROCm execution provider. This is something that Microsoft, like a bunch of our engineers contributed, built the ROCm execution provider. And then we are happy to receive contributions from AMD on the MI Graphics, which is the inference, whereas the ROCm execution provider supports both training and inference. And like I think if you look at the stack for the Onyx Runtime, it supports like you take your deep learning graph and then you break it up into all these like various partitions and find the most efficient way to schedule these across the GPU hardware. And then it interfaces with the execution providers, which in turn kind of directly talk to the actual hardware, implements the best instructions that can be for this particular operation, for the shapes of these matrices that you're talking about. So that is about the Onyx Runtime. We've been offering it since July 2021. And MI Graphics has been there even before that, February 2020. And we are publishing like nightly packages. So right now consuming these are pretty easy, and then also stable packages. So if you have like things that are like a little bit more kind of tested in a more integrated fashion, so we use the you can use a stable package, or if you want to use the most cutting edge, the latest optimizations, use the nightly package that we provide. So the next one I want to kind of quickly talk about is DeepSpeed on ROCm. Again, this one was, I think bulk of this work was actually done by AMD engineers. and they have, I think there was a separate branch that I think all the it was being supported till like around March 2022, and then in March I think it was all like upstreamed into a single source. So the same thing, like exactly the same kernels that were written for CUDA. We use all the hippification, all the stuff that you talked about. We use that, and then it's integrated into the pipeline. And then like we have like nightly build setup, like unit tests are all passing, and then so I think at this point like there is no API changes required, and like you just install it as like you would install on an NVIDIA hardware. Like you do pip install deep speed, and it will automatically pre-compile the kernel, automatically under the covers run the hippification, and then install all these kernels, and it's pretty much ready to go. And deep speed is like I think pretty much a lot of our internal workloads, as well as when you talk about like outside, whether it is customers using the Hugging Face Transformer library or PyTorch Lightning library, Mosaic ML, like all these very popular packages use deep speed for accelerating like all their workloads. Then you can see the number of contributors. It's a pretty big list of contributors here. So I think we thank like all the pretty healthy ecosystem, and glad to see AMD contributing pretty heavily on that.
Very cool.
I think next I want to talk about a few research framework. The first one I want to highlight is a package called MSYCL. So many of you may be familiar with NCCL and AMD's equivalent called RCCL, which allows you to do all the collective communications. And where I think MSYCL is a research project from Microsoft Research, where it allows you to write your own custom, in addition to the standard algorithms that are provided by the respective vendors, like the ring algorithm and tree algorithm. You can actually build your own custom algorithms, and those algorithms are based on your topology of your hardware. Like if you're using PCI for communication, or are you using a standard Ethernet or InfiniBand, and then depending on the size of the matrices that you're shuttling across the network, it can pick the most appropriate algorithm. And Axel, I think if you want the best performance, you should be using something like MSYCL. And also happy to hear that AMD has actually integrated MSYCL into the RCCL. So you can actually
say that I saw MSYCL in the RCCL code base. Yes.
Yeah. No. So it's an option. So if you want to use a standard algorithm provided by AMD, like tree or ring, you can use that. Or if you want to build your own custom algorithms or discover custom algorithms for your specific hardware topology, you can use MSYCL, and it's DSL based, so you can actually it's an easy way to specify your topology. There's configurations, and we package a bunch of custom algorithms which are like very specifically tuned to the Azure hardware configuration of the AMD GPUs and NVIDIA GPUs. So it supports like multiple platforms. So we bring like parity to all those across, and this is the good thing is it's all open source, so you can use it yourself. And the custom algorithms are already tuned for like Azure, so you don't need to like we have done all the work, so customers don't have to do all those work. One related software to MSYCL is called NPKit. So again, this is work from our MSR Asian team. And so this provides a much more fine-grained profiling. So like normally when you look at the profile, you get like a top-level operation. Here you can peek down like 1 or 2 levels below to see like each of the data movement and kernel launches. So you can actually look at a much more fine-grained level of profile that we ourselves had been using. Like our MSYCL team was using it to debug their code. And now we have actually open sourced it, and then when you compile RCCL, now there's an option, okay, compile it with NPKit, and you get all these this fine-grained profiling, which would help you in as you build your custom algorithms and or just debugging performance problems. I think these debugging any type of distributed system is incredibly complex. So the more you are equipped with all these tools, I think it helps you. Third thing, again, this is another distributed metrics collection agents. So it's able to collect metrics from CPU, GPUs, like all our fleets, and we use that to manage our entire fleet, and then publish it into a standard-based framework like Prometheus to do the matrix collection, and then use Grafana for like all the dashboards. So pretty standard stuff, but I think we have kind of consolidated all these things. Like you get like a single pane where you can see all these things. Then, like last but not least, I think Superbench. This is one of our earliest contribution from our Microsoft research, where you can run a whole bunch of micro benchmarks. Like you can look at your compute benchmarks, like the flops, some profiling, like different operations, memory operations, and some communications. So we again open source that where you can actually compare it, run it on like across your hardware. We also use it to monitor the health of hardware. So when new hardware comes from a repair, Azure uses it to kind of see that, okay, like it performs as per specs. And this is something that you can find on GitHub. Then we use it, and it also supports model level benchmarks, like all the popular models, whether it's like ResNet, BERT models. So you can run this with like different options. Like I want to run it in FP16, BF16. So you can compare how these models perform on like different operations and across like single node, multiple nodes, distributed training. So it supports everything. And again, this is just a very tiny sliver of the open source contribution that Microsoft has made. And all these things, we use it internally quite heavily to run all our workloads. And here's a few more. I think MOE is a mixture of experts. So we have an open source project called Tutel, which I think which is integrated into the Meta Facebook's FairSec library, for example. And then we are working on the mixed precision. I think it's going to be open source pretty soon. It'll support the floating point 8-bit format, which is FP8, which is pretty new. So I think these are all just give a little bit flavor into the like some of the open source contributions, and I think ROCm itself being open. And I think the open collaboration that we have with your engineers, I think makes all these things possible. And I think it was kind of really joy to kind of work on these and make it available to the community.
That's fantastic. So one of the things that will be interesting is looking at the Azure Stack, as well as potentially other teams and what other folks are doing on AMD hardware. Do you have other workloads we can talk about?
Yeah, I think let's talk about the stack first. Okay. So this is what I think it's a little bit, I think you alluded to that. I think this is our version of that, I think what you present. And this is what like all the workloads that are using our current cluster of thousands of GPUs are actually using. So at the bottommost level, we have the Azure infrastructure, which supports virtual machines, virtual machine scale set if you are building like a cluster, as well as like Kubernetes. Azure Kubernetes Service supports both AMD MI250X GPUs as well as NVIDIA GPUs. And then we have the Azure Machine Learning Platform. So the platform itself, look at it as kind of a two major areas. So one is on the top level, you have the dev experience. At the bottom level, you have all the infra management. So you have a fleet. So each of the teams, we allocate them a bunch of GPUs, and you have to manage that fleet and how those jobs run on those fleet. So that's a job of a GPU scheduler. Obviously, there are custom, there are open schedulers like Slurm. Internally, we happen to use like the Azure Machine Learning. We built our own scheduler, and we even published archive papers that has some more advanced features that we need for large-scale installations. So that is the Azure infra management piece. And then on the dev experience, like Azure Machine Learning provides like doing experimentation management, like having a dashboard for your responsible AI. Like I want to test these things, whether they're going to output something harmful, and then deployments. So you can train a model, and then you can actually, with the one click, you can actually deploy these models. So store them in a registry, have a catalog of models, and then so all those things are provided by the Azure Machine Learning dev experience. We also provide something called Azure Container for PyTorch. We predominantly we use PyTorch internally for all our workloads, and so we build a Docker container, a standardized Docker container that has like all the popular software that we use. Like I think we talked about Onyx Runtime, we talked about DeepSpeed, MSQL,
Right.
OpenAI Triton. So Triton is another software that's used to if you're writing your own custom kernel, and then the actual PyTorch. And then at the bottom level, you have all the libraries that you already talked about. So all these things we kind of take care of testing it, and then ensuring that all the versions are all compatible. And then we publish like periodically, like every few weeks, we publish like new versions of this container. So that way, I think people can get started. You don't have to figure out which version of PyTorch will work with which version of ROCm. So it's so we make all that stuff easy. And Azure Container for PyTorch is also currently it is available for all customers of Azure for NVIDIA, and then soon I think it will be internally we have a version for AMD, which I think we hope to offer it as a product to outside customers. And then when you go to the top level, so you have the PyTorch ecosystem apps. So you can just write plain PyTorch application that you bring, or use some open source trainer framework like Hugging Face Accelerate framework, or or the like I think a lot of people pre-training the models. I think people use the Meta's FairSec. So we support all that because anything built on the top of PyTorch automatically like you get some level of hardware independence. And I think in your list also you had a whole bunch of experimentation management frameworks. So you can bring in your own management framework if you don't like what you have here in Azure. So essentially, it's a platform. You bring what you are comfortable with, and I think out of the box, Azure Machine Learning provides a whole bunch of feature functionality that you can build your own Azure Machine Learning apps using the SDK. And then for more complex orchestration, we provide an Azure Machine Learning pipeline. You have like a data processing pipeline feeding into a machine ML training pipeline, and then into a deployment evaluation and deployment pipeline. So you can chain all these things together into this visual some pipeline, and so we provide both a visual as well as an SDK-based approach to constructing your own pipelines. And then finally, you can use just command line interface, like Accelerate has a CLI, PyTorch Lightning has a CLI, and Mosaic ML. So all the you can use any of these CLI, and Azure Machine Learning itself provides a CLI interface where you can submit a job, you can look at logs from the job. So I think cool. so that's kind of at a high level what our stack provides. One other thing I wanted to kind of cover, like in terms of the actual scalability of the platform. So one of the things that we also ran is, I think, a bunch of scalability experiments late when we kind of built it. So we were able to run it on up to like each node is like about 8 GPUs. So we ran it on up to like 128 nodes, which is like about 1,000 MI250. So it's a pretty large scale. So as you see on this diagram, on like synthetic workloads, you see like almost like linear scale up when you go from like I think something like 16 nodes all the way to like 128 nodes. And then even with the real data, you can actually see that it's quite linear, and then it's slightly starts tapering off. The main difference between synthetic and real data is, I think, the shapes of the matrices vary like a lot more in a real data. Whereas in synthetic data, like I think things are a little bit more constrained. But overall, this is a pretty large model for generative vision vision transformer models. So I think we got pretty good results on this on scaling. So once So I think let me go into the actual workloads that that we've onboarded. So again, this is not a full exhaustive list, but I think as I mentioned, our goal was to run all our top tier workloads. So these are all some of the among the top workloads. So obviously Bing and our web experience team uses it for like inferencing as well as for training.
Okay.
Like for example, on inferencing, we use like you want to take billions of documents and then do some kind of a semantic indexing on them. So it's an extremely compute intensive job, and then continuously we keep getting documents and we have to catch up like every day, right? To kind of do this inferencing. These are all like near real time, but I think like high performance and throughput is pretty important here. Weather was another like cool application. I think the Bing has a weather feature, and the weather team builds like weather-based models. And then the search relevance teams, they build a bunch of language models and run multiple experiments. So they're always flighting new experiments in production. So this allows them to rapidly create these models, have some kind of hypothesis, flight them, and then figure out, okay, hey, which button should I tweak to get better, higher relevance on your search. Developer division, I think they built some NL to code models like Code Llama or Code T5, like formula, like generating formulas for like Excel. Or repairing the code, like I think you generate some formulas, you want to repair those some formulas. So all these things are done. I think they've been able to run these models on this AMD cluster that we have. Nice. Next, Microsoft Designer. It's a pretty cool product. Whether you're I don't know, building some kind of a invitation card for your kid's birthday, or you're designing some marketing brochure. So here they built some segmentation models and like image to image similarity models. So here they built both traditional convolutional neural network model as well as like transformer based models in this domain. Speech and language, obviously I think like what you see on the top, those are all like served by the speech model. So those speech models, they experiment with like multiple architectures, constantly evolving those algorithms like RNNT, and then for the language part, like Llama 2, doing some fine tuning. And then finally, like cognitive service vision, I think they have trained vision models as well as like multimodal models where you can answer visual question answering or captioning. So you give an image and then get some automatic captioning for that, and kind of combination of again more traditional convolutional neural networks as well as a combination of convolution and vision transformers.
So if I look at this list, it's pretty representative of pretty much everything you would want to do, right? It's from language model to vision, pretty representative list of.
Yeah, no, I think again the portability of the stack. I think like we were still a pretty small team, kind of supporting these. We were like that thanks to the portability that the AMD stack provides. I think people were able to get it up and running pretty quickly, and then move on, run with their experiments, and then engage with us on kind of performance optimization and stuff like that. So yeah, again, this is just a small sliver of applications covering pretty whole gamut of like all the applications that you can kind of think of.
Right.
And so I think, yeah, we feel comfortable that yes, this is ready for like prime time. Cool. And that's where I think the announcement that Satya made and all, I think, yeah, it all makes sense. Yeah, in the context of all these things, like I think any new platform comes with its own set of friction learning curve. By running these, I think, yeah, we hope to kind of minimize some of those learning curve involved, and then the stack itself. Just a few more things I have. Our research also uses this cluster. So here are some papers. Like I think the first one is like the Excel formula, and then one of the team that research team they trained this model on like 512 GPUs. As an alternative to like what is next to transformers. So like people are researchers always thinking about what is next, and this is one of the models that they also ran on the AMD, and they got pretty good results on this. And then the last one is like a translation model, machine translation. So you translate from one language to another. They were able to actually take the Llama 2 model and then fine tune it, and then get good results in like 10 different languages. I think it performed pretty good like state of art results on that. With a relatively modest, like these days, I think 18 hours on 16 GPUs is actually pretty considered pretty modest. Yeah, like even 1 year or 2 years back, this would have been a pretty big.
That's a big cluster. Right?
Yeah, but I think today it's still a pretty modest kind of requirement that I think many teams have access to these type of this one. Yeah. All right.
Some demos. Let's go.
Yeah, I think one of the things I just want to show you kind of a quick demo for like how to take something like I think take an open source model. So I ended up like Meta published I think about a few months back a text to music model. Like I'm an amateur musician myself, so I'm always interested in this particular area. So they built this model called MusicGen. So I thought, well, like, what would it take to just run it, right? Like, what steps do I need to do to just get it to run? So here is my actual, like, I'm going to show you like exactly, like I have almost like a bare machine which just has a GPU driver on it, nothing else, and I'm within a container. So let's just spin the demo here. So I'm in a console. So I'm creating rock music.
You're testing my drop-in replacement claim here.
Yeah.
Gotcha.
Yeah, I love rock music, rock M.
There you go.
See the
connection.
Yeah, I see the connection there. So,
okay.
So I activate, and then I first install the torch, which is available on pytorch.org. So this is something that you pick up the wheel automatically from a host that the pytorch.org is hosting, and then I sped it a little bit.
So this is all I was going to say.
Yeah, and then
pretty fast internet.
Yeah, so here's where I pull the actual code from Hugging Face.
Okay.
So I just clone the repo and then install the requirements here. So a few packages it just installs, and yeah, in a few minutes it will be done. Yeah, I think I just sped up some part of it, I think, but otherwise this is exactly what it takes.
So nothing's different here, right?
Nothing too fancy. I think there I have to deal with some specific version, but otherwise I think like and here I think we just run. What happened here? Okay, yeah, it's running. Python abdo.py share. So this is a Gradio app. So many of you are familiar with Gradio. So it essentially publishes a URL where I can actually hit from anywhere on the internet. So you can actually see that Gradio will be so spinning up. So you see that there's a URL. So I'm going to click on that. That click means this click here.
Very cool.
So here, so this is what the Gradio interface looks like, and then so let's play this. So I'm going to pick a prompt that says, so you give a text prompt and then ask it to generate some music. So here, like I don't want a country song, I want a reggae, I'm a reggae fan, and then I want some music for the holidays to entertain my guests.
Reggae holiday music, okay.
So here, is it really running on a GPU? Yes, so it has loaded the model. So you can see that the GPU is 82%. It's only taking like about 10% of the GPU. Like each GPU has like 64 gig of memory. So you can run like pretty much a lot of load. I can actually run a service on like a single GPU here. So now I think, so very soon I think, you can actually see that it's actually generating this model. So again, this is again a transformer model, single stage. Okay. Pretty good reggae music, I think.
Not bad.
But rocking on this.
Very, very cool. That's awesome. And so the nice thing about that was it was just pip install all the way through. Like.
Yep, I think that's pretty much it. Yeah.
Git clone pip install. Yep. Yeah. That's fantastic.
Yeah, and then we've also been running other models. Like I think today, I think Satya mentioned in the keynote that we are working on getting GPT-4 running on it. We already have like DALL-E running on in our labs. So again, any guess? Like one of them is generated from on an AMD and another one is generated from production. Oh any guess which one would be what? Left or right? Left or right?
Any guess? Actually, I have no idea.
Okay,
Left?
it's the left. Okay.
Oh, that is more brighter. Okay.
Yes, and then one more example here. Yeah, so I think, yeah, you see that, yeah, again, the one on the left is from AMD. The other one is from our production. In fact, I think I like the detail on the on the left.
Aha. So Satya mentioned this morning in his keynote, the availability of the 300X, and I happen to have one here with me. I'm going to do a Steve Jobs. So this is the 300X. It's a phenomenal GPU. We're running this in our labs now, benchmarking. Any feedback on what you expect to see?
Yeah, no, we are very excited with the high capacity and the bandwidth that it's providing. So it's going to be a pretty good game changer for large model inferencing and fine tuning. So yeah, I can't wait to kind of get our hands and offer this to customers like sometime next year. Yeah, soon.
Awesome.
Yeah.
Fantastic. Thank you so much, Gopi. Thanks, everyone.
Thanks, Vijay.